We're now going to have Dieter Amay from the RWTH Aachen in Germany. He was one of the early users of the Niagara system, and I think he has very interesting results for us to share. Dieter?
So, good afternoon. Which one? This one? Okay. Even more comparisons, even more performance benchmarks of the Niagara system, the UltraSPARC T2 as it's called today. I had too many slides, so I have to run a little quickly. It's only 20 minutes. So I go into architectures, not of the Niagara 2 that much, but I'm comparing the systems to other systems. Right now we're still running a lot of these big Sunfire servers in our centers. They're getting old, they're consuming a lot of power, and we're interested in replacing them. The question is with which kind of systems. So I'm comparing the Niagara to some other boxes. I will look at a few kernels, at a few applications, look at throughput and at power consumption before I come to a conclusion. Here. So the disclaimer is everything is preliminary. The box that we had access to was pre-production. It has been upgraded, but the firmware has been upgraded during that time, which made a difference to some of the experiments, not to all of them. But you never know. So those numbers are may change in the future. And so we just didn't look into the details very much. We were interested in what kind of codes run well on the system, what kind of codes do not run well on the system. This was our big focus, was the big picture. So these are the machines that we looked at. So we had these big servers, Sunfire 2900 and 6900. They have UltraSPARC 4, 1.2 gigahertz. The 2900 had 12 of these dual core chips, the 6900 24. Then we are running an Optron box. It's not the latest one. It's a 2.2 gigahertz dual core quad socket system, so 8 cores in total. It's 2 years old, so a newer system would be more interesting, and a Barcelona system would even be most interesting to look at in comparison. We have quite recent Dell machines there with Clovertown and Woodcrest processors. So very fast shared cache architecture with a known memory bottleneck. And then we ran the Niagara systems. We ran Solaris 9 and 10 and the latest studio compilers on the big servers and also on the Optron. And we ran Scientific Linux on the Dell systems and Intel 9.1 and 10.0 compilers. So this is now just a looking at comparing the processors. So the Spark is 2 cores, the Optron was 2 cores, the Intel was 2 or 4 cores, and Niagara is 8 cores and 64 threads. The gigahertz rate differs quite a bit. The old UltraSPARC is 1.2, the Niagara 1.4, the Optron 2.2, the latest one are 2.8 as far as I know. The Intel processors are 3 or 2.66, the Clovertown is running a little slower. So if you look at floating point down here, the systems differ quite a bit. So here the processor of the Clovertown is 40 gigaflops versus 11 here the Niagara, so there's quite a range, and the UltraSPARC is 4.8. It's the technology difference, so the UltraSPARC is 2 generations older. So actually the best comparison here is the Intel chips to the Niagara right now. Cache size is comparable here. We have these large caches on the UltraSPARC 4, but they are off chip, whereas on the other systems the caches are on chip. Now looking at the full boxes, on the left side the old box is a full cabinet. For the 6900 it's a third of a cabinet for the 2900, whereas these systems are very small, 1, 2 unit, 3 unit boxes. The big servers, as I told before, 12 or 24 chips. Here we have 4 chips, 2 chips and 1 chip here. A lot of cores, 24, 48 cores, 8 cores. 4 or 8 cores here and 8 cores here. So we are comparing really different systems. Floating point performance also differs a lot. So just looking at the 11 on the Niagara versus 85 at the Clovertown and in between here. Of course, the capacity of the big boxes is very high if you tune it well. Also, the memory is quite different. Of course, the big boxes have 48 or 96 gigabyte, and here we have oh, this is, let me see. This is wrong, it was 32 gigabyte here, so this is wrong. And 16 or 8 on the Dell systems. Okay, So looking at some experiments, of course, for HPC applications, memory bandwidth is always an issue. So I had this very tiny kernel, which I used only also for the Niagara 1. So I wanted to use this because there's no floating point involved. So I'm fetching a vector, basically doing some integer operation, and then I'm storing the same vector. This is what I used. We ran this kernel with multiple threads, working on private data using OpenMP. We have a large memory footprint, so we don't want to look at the cache performance here. We used explicit processor binding to pin threads to the cores. So there is a lot of details. So I could talk like an hour about these experiments. So just this is the overview of the experiments here. So with one thread, we see that the Intel processor is doing very well. So they have about 4 to 4.6 gigabytes per second with one thread. On the Optron is 4 gigabytes per second. The Niagara is 1.2, and the UltraSPARC is 1.6. Now, if I increase the number of simultaneous threads here, the picture is getting very different, and we see a range of numbers here. And this is particularly true for the Optron system and also for the Intel systems here. So why is that? So the Optron, you know, it's a CC NUMA box, and it depends pretty much on where your thread is running and where your data is located. So you have a range of numbers. Do we have a pointer here somewhere? Not the case. So for example, down here, the Optron, you see if you run 8 threads and you don't have your memory at the right place, your data at the right place, you only get 4 gigabytes per second. Whereas in the optimal case, you have 18 gigabytes per second. Same is true for the Intel boxes here. With 2 threads, for example, there's a range between 4.7 and 7.9 here, and 4 and 6.9 here. So if you run 2 threads on these Intel boxes, you really need to look at where the threads are running, if they share caches or not. Versus the SPARC boxes, the old one, and also the Niagara here, they're not so sensitive to placement here. So the ranges are much smaller. I get the best memory bandwidth when running 16 threads here. It's going down a little bit with more threads down here. But as a whole, the memory bandwidth that I obtain here is about 15 gigabytes for one chip, versus here I have 2 chips, and there it's 4 chips. So the per chip memory bandwidth is best on the Niagara here. And this is actually kind of interesting. I mean, I have a history in vector computing, and this is always an interesting number. So I would say that the Niagara is, for the first time, a low-cost vector type of processor with respect to memory performance. So another kernel is the Linpack, and here you can see, of course, if you have a code which consumes a lot of floating point numbers and can be well optimized, so you could do a lot of cache optimization, then of course the Niagara is lost, because the number of floating point operations that you can achieve is limited by 11, so I measured about up to 9 here, whereas all the other systems, they have a much higher peak performance, which can be obtained if it's properly tuned. Another kernel I'm looking at here is a sparse matrix vector multiplication. This is particularly interesting for our applications, versus the Linpack is not very interesting for our application, but this is because the sparse metric vector multiplication is in the heart of very many PDE solvers, and actually this is a part of a bigger code, and also the matrix that we used here is a real matrix out of an application code here. So it's also parallelized with OpenMP over the number of threads. I plot here the megaflop rate or the gigaflop rate, megaflop rate here. And what you can see here is that the Niagara 2, so the UltraSPARC T2, really outperforms all the other boxes that we looked at. So it scales extremely well. And the interesting point is it scales better if I have more than 64 threads. And that was astonishing. I couldn't believe that. We discussed it with some of the Sun experts. And so the best I got with 112 threads here. So we looked at counters at this core start, and actually the floating point unit utilization is best here. So which is really astonishing. So you can see that here the other, so this is the Optron is doing pretty well because of the nice memory bandwidth. And we took care of the CC NUMA architecture, so memory placement is optimized, and we did all play a lot of tricks. So this was kind of interesting. So what you can see is that I'm getting here 28.7% out of peak memory, out of peak floating point performance on a code which is very bad. It has indirect addressing, so the other processors don't really like that. Okay, looking at applications, I gotta speed up a little bit. This is benchmark code, Navier-Stokes solver, parallelized with OpenMP. Okay, great. Yeah. Parallelized with OpenMP on the loop level, so its scalability is limited. This is a logarithmic scale here, as you can see. So all the other processes, machines, they scale to some degree, but they're kind of fast. This is runtime. So the Niagara starts very slow, but speeds up a little bit. But as the scalability of this program is limited, it can catch up. So for this application, the others are doing better. So this is not throughput; it's single application. If I have the same code, same benchmark code, but here it's parallelized on two levels with MPI on top and OpenMP underneath, there's more room to catch up. So here's the number of processes times the number of threads that I'm plotting here. So when I have more room for parallelization here, then the Niagara system catches up. Only the UltraSPARC 4 box, the big box, is doing better here. So this is also logarithmic scale. So this is the same code, a large data set. Now I'm comparing a 2900, the UltraSPARC 4 box, with 24 cores to the Niagara system. And I'm playing with a number of processes, so it's hybrid again, so MPI on top, OpenMP underneath. And I'm playing with a number of MPI processes versus the number of threads underneath. The problem always, when comparing these machines, if you have such codes, you always do some kind of fine-tuning and selecting a good number here. And if you really compare this code on multiple machines, you want to optimize these settings here. And this is what I did. If I only turn on parallelization on the lower level, then, for example, on the UltraSPARC 4 box, I do well up to 22 threads here, and I obtain 59 seconds. On the Niagara box, I'm doing better with, now let me see here, with 32 threads on the lower level. If I turn on MPI on top, I obtain here with 8 processes times 3 threads, I have 37 seconds. On the Niagara, the best I can obtain is 16 MPI processes and 4 threads each. But in any case, this small Niagara outperforms the 2900. Now the same code again, but now in an application setting and simulation to flow through the human nose. This is an application, it's a little bit different version of code, which we really try to optimize for a number of boxes, really squeeze out the optimal performance. It's parallelized with OpenMP on 2 levels. And the same thing, so we have to adjust the number of threads on the high level and the number of threads on the low level. And there are a bunch of strategies that we use to optimize it per system. We try just to squeeze what we can get out of the machines here. And here I used another box that I didn't have in the list initially. This is the Sunfire 25K, which has 72 UltraSPARC 4 processors. So here the best we could achieve was 64 threads on this box because the scalability of this code is limited. We have load imbalances and all kind of problems here. We ended up with 20 seconds for this application here, 8 times 8, 18 seconds, sorry, this one here. The speed up is 20 for 64 threads here. So on the Optron, I have the Optron is 26 seconds here with 8 threads on the higher level and 1 thread on the lower level. Interestingly, this code has been developed originally for a vector machine. It still performs excellent on a NEC SX8 system. So I have 15 seconds on 1 vector processor here. And it takes me like 64 cores on the UltraSPARC 4 to obtain 18 seconds. So I'm still far away. Which means vector systems are still interesting for these kind of codes. And you can catch up with on the other boxes. And now I looked at the Niagara system, and on the Niagara system playing all these tricks with 4 threads on the higher level and 16 on the lower level obtained 24 seconds. So it's almost the speed of the big boxes. I think it's quite interesting. It's still away from a vector processor, but also concerning the price, it's still away from the vector processor, which I find interesting. But and on the vector, I can use the OpenMP as well. but the speed up is limited, so I only have 2.7 speed up on up to 8 threads. Actually, I used 8 threads here. Okay. And I made the first experiments on the Victoria Falls, and it's doing a little bit better even than this box. Flower and Navier-Stokes solvers, same impression. So here comparing the 2900 and the Niagara. The Niagara is doing better with the optimal combination of MPI processes and OpenMP, so another hybrid application. So we have a bunch of applications. I'm only showing a few, but of course there are applications where the Niagara does not perform as well. So this is contact analysis of bevel gears. It's a lot of geometry processing, so it's very cache friendly. This application scales well, so this is scalability with OpenMP on all the boxes here. But it performs, if you look at the megaflops, this is the megaflop rate here, it performs much better than the Niagara, and the Niagara is here. So it scales well, but it starts very slow compared to the other boxes. It scales well, but it comes to an end, of course. So probably scalability could be better here. But here, the Intel boxes and the Optrons also really dominating because of their excellent cache performance and higher cycle rate. So basically we have two extremes. So there is a class of applications where the Niagara does excellent, and there's another class of applications which are very cache friendly, where you see the Niagara is doing not so well. And if you now look at throughput, and throughput is, as I defined it, is the number of instances. I'm optimizing throughput by varying the number of instances that I'm starting on the box, and I try to find the optimal number of instances divided by the average runtime. So here I'm comparing the 6900, the box which we wanted to replace. We have 16 of those, so it's kind of interesting to look at this, comparing this to the Niagara system. Here I run this TFS Navier-Stokes solver parallelized on the loop level with 8 threads as one instance, and I vary the number of instances that I'm starting at the same time, and then I plot here the throughput rate. So high is good. And you can see that here overloading the systems, in both cases the 6900 but also the Niagara, overloading the system pays off. And here the Niagara outperforms the 6900. Why is that? So here I have an explanation, because it's loop level parallelization, and the parallelization is not perfect. There's still serial regions in between, so they can overlap. And so I can get a better throughput by overloading the box here, basically. This is different, so I have to let the threads sleep if they're not used to get this performance improvement with many instances. The same is true for the hybrid version of this code. It's a little bit more variation, which I cannot explain so far, but here they are performing pretty similarly, and also overloading is okay. The other application, which is very cache friendly, you can see that clearly here the UltraSPARC 4 base box performs very well because of these large L2 caches, 8 megabyte. So the application basically fits into the L2 cache, and here all the threads, they have to share one L2 cache, so they perform with memory speed basically. So if you look at throughput, and here I also add the Optron and the kilowatt-hour system, so the Intel boxes. Here I only have one instance because overloading the system doesn't make much sense. I see that the Niagara system for the good code, for the good one, performs as well as the big 6900. It performs worse for this cache-friendly application. And for the cache-friendly application, of course, these Optron or Intel boxes perform much better. The difference is roughly a factor of 2. So throughput is better on Niagara compared to Optron and Intel boxes here, both 8 cores. And it's a factor of 2, and for cache-friendly, it's also a factor 2, but the other way around. Now looking at power. So we made some power measurements here. We fully loaded the boxes and measured the 6900 with 96 gigabyte at 6.5 kilowatts. So that's a lot. And when it's idling, it almost consumes the same 90%. The 4 Optron processors here is 500 watt. The Clovertowns, the 2 is also 500 watt. The Niagara is almost 400 watt. And if they are idling, they consume less power. But this is normally not the case in our center, so these are the interesting numbers. So the difference is huge, of course. So if you now calculate the performance per power consumption, this is the memory bandwidth program. It's a stream that I run here, then the Niagara is doing pretty well. It's roughly a factor of 2 better than the other systems, and of course much better than the old one here. Also factor of 2 compared to Optron and Intel here. And for applications which run well in the cache, it's the other way around again. So here the Intel is doing best and Niagara is doing not as well. But still they all do better than the old ones, of course. Throughput per power consumption here, it's roughly this factor of 2 or 3 that I see here for the TFS code, which consumes all the memory bandwidth. The Niagara performs better per power than the Optron and the Clovertown-based systems, and for this cache-friendly application, it's the other way around. So this brings me to the conclusion. Obviously, a combination of Niagara 2 and Clovertown-based system is a very attractive option to replace the old boxes, and provided that the application are really directed to their appropriate platform. And of course, it's now our job in the computing center to support our people and give right advice where to submit the job in future. Of course, we are looking at hardware performance counter to characterize an application. And this AccuMem tool that Eric Huggerson presented in the morning is very helpful to characterize the cache performance of an application. For example, this is a screenshot of an analysis of this bevel gear simulation program, which is very cache friendly. You can see that with some 8 megabytes of cache size, I basically don't have any cache misses anymore. So this tool is very helpful to characterize applications and then decide which way to go. Interesting, of course, is, and that is still open investigation, how many threads or how large should the load be on a Niagara 2 system. So how many threads do you want to start for your application? And this varies pretty much from application to application, and maybe also these charts may be very helpful to find out where are there sweet spots in the application to place this. So with this, I'm done, I think, and there's more information. So I set up a web page which describes more details about this comparisons of the machines and the Niagara 2. Thank you.